All right, sports fans, welcome back. We are on to lesson 12, which is relations and functions. Essentially, a relation is any combination of inputs and outputs. So we're going to have x's and y's, where x's are our inputs, y's are our outputs. And no matter what those x's and y's are, it is a relation. And we say there's a relationship between x and y. But a function, on the other hand, a function is a specific type of relation that follows certain rules. So we're going to see what those rules actually are. But before we get to what a function is, first we're going to talk about domain and range. Okay, domain and range is just identifying what the inputs and outputs are. Then we'll determine if the relation is a function. We'll use something called the vertical line test, and we will find values of functions, meaning evaluate the functions for certain values. Okay, and then what we're trying to build up to here. Our application says the number of tacos, T, consumed at a restaurant with a number of customers, P, is given by the function T equals f of P. Last week, the restaurant workers saw 6,000 tacos get consumed by 2,000 customers. Express this information using the function f. So what we're going to want to do is just essentially say in function notation, what do the 6,000 and 2,000 represent? And then we're going to explain the meaning of f of 2 equals 6. So we'll say what this f of 2 equals 6 actually represents in words. So essentially this explain part is the opposite of what we're going to do in part 1. But we'll come back to that at the end. So first things first, domain and range. A relation is any set of ordered pairs, x comma y. The set of inputs, which are also known as independent variables or x values. Okay, so remember, x values are independent, and those are called inputs. We call them being independent because we are choosing what we input, so it doesn't depend on anything else. We just get to make a choice independent of any other situations. So the inputs are independent, and those are the x values. Okay, and the set of all x values, or all inputs, we call the domain of the function. So everything that you can plug in is the domain. On the other hand, the set of all outputs are known as the dependent variables or y values. We call them dependent because the value of y, so these y values, depends on what we plug in for x. So I can't tell you what y is until you tell me what x is, because y depends on x. The outputs depend on the inputs. All right, and the set of all those outputs is called the range of the function. Okay, so now we're going to actually talk in deeper about domain and range in the following lesson. Okay, we'll talk about what can be plugged in, can't be plugged in. For right now, though, we're just going to identify what the domain and range is based on these ordered pairs we have. So every time we look at an ordered pair, we should know from graphing that this represents an x and a y. So each of these ordered pairs is an x and a y, x and y, x and y, x and y, x and y. Our job right now is to identify the domain and range, where we will label the domain with a big D and the range with a big R. And we're going to say the domain is equal to and the range is equal to. So big D equals, big R equals. And for each of these, we're going to have a set of points. So when you write down a set, notice the way the ordered pairs are given as a set. There's these braces on the front and the back end. Okay, so those braces tell us that we have a set. So when we list out the domain, we're going to write it as a set, which means we put squiggly braces on each side. Okay, so both the domain and range are sets, so we use those squiggly braces. And then we just say what elements are in each set. The domain is all the x values, and the range is all the y values. So for domain, our x values are 1, 2, 3, 4, and 5. Just looking over here, 1, 2, 3, 4, and 5. So I can go ahead and copy those in. I put commas in between each one because they are all elements of a set, so they need a comma to separate them. And the range is all the y values, which go 2, 4, 6, 8, 10. So all I do is copy those down, 2, 4, 6, 8, 10. And that's all there is to it. Identifying the domain and range just means listing out the x values and y values. So you should be able to do that. Go ahead and try the second one. Pause the video. All right, hopefully you paused. So when we list this out, the domain is going to be equal to a set, and the range is going to be equal to a set, where again we use big D and big R to denote domain and range. The squiggly braces I already drew are to put the ordered pairs into individual sets, where the domain will have all the x's, the range will have all the y's. And then now we just list out the x's and y's. So the x's are 1, 2, 3, 4, and 5 again. 1, 2, 3, 4, and 5. And the range this time is 4, 3, 7, 9, and 1. 4, 3, 7, 9, and 1. Some professors are going to be real nitpicky about how you write your set. So a lot of people will tell you to rewrite the range here in order. So 1, 3, 4, 7, 9. However, it technically does not matter. Okay, so it's better notation to write it in order because it makes it easier to understand what's in there. But technically speaking, each of those answers is just as good. And so I usually just write it in the order I see them in, which is the first option. But it's better if you write in the second one, okay? So the second one is better when it is in order. All right, now functions. A function is just a special type of relation, and it's a relation where each possible input value leads to exactly one output value. So for every x, there is one y. Okay, and we say that the output is a function of the input. Meaning if you tell me what the output is, I can tell you what the input was that gave it to me. So another way to say it is every input has exactly one output. So every x goes to exactly one y value. Okay, if we have one x goes to one y, then this is good. But if we have one x goes to two y's, so y1 and y2, this is bad. Okay, so each x has to go to just one y value. We can't have the same x go to two different places. All right, so now the notation we use is y equals f of x right here. This defines a function whose name is f. So notice f of x, the name is f. And we say it y is a function of x, or y equals f of x, where we say of x, okay, because we're plugging x into the function. The letter x represents the input values, which are again the independent variables, and the letter y represents the output values, which are the dependent variables. So from the last slide, we know that the first thing is the domain, the set of all x's, and the second thing is the range, the set of all y's. All right, so now we're just going to figure out if each of these tables represents a function or not. And all we have to do is check what I put up here on the top right. Does each x go to exactly one y? Or is there an x value that gets split and goes to two y's? All right, so let's see what happens. In the first table, -4 goes to 0. All good. 3 goes to 1. Still good. 5 goes to 1. Still good. 7 goes to 8. Still good. And 10 goes to 14. There was nothing that breaks the rule there, so this is a function. Okay. Notice that the x values were all different. Okay, we never use the same number twice over here. And so there was no way any of these could have gone to two different places because each of them only showed up once. So this case I drew over here on the right, where one x goes to two places, you would have to see the same x twice in order for that to happen. But in this case, we had different x's the whole time over here on the left. And so no x goes to two different places. Notice that 3 goes to 1 and 5 also goes to 1. That's okay because two x's can go to the same place. So two inputs can go to the same output. We just can't have one input go to two different outputs. Okay, so let's see one that is not a function now, so this makes a little more sense. The second table, -2 goes to -3, 3 goes to 2, and then 3 goes to 6. So without even looking at the next couple, we have the same value here, 3, going to two different places. So if 3 goes to two different places, just think about if 3 is a person trying to go to two different houses at the same time, you'd have to rip 3 in half. It's just not possible. So same thing with functions. We cannot have the same input go to two different outputs. And so because of this, these two 3's going to two different places. This is not a function. All right, third table. We have -2 goes to 0, 2 goes to 3, 5 goes to 6, 7 goes to 9, 11 goes to 15. Notice none of these x values got repeated, so we're all good. This is a function. Okay. Again, if you don't use the same x value twice, you're not even going to have to worry about it. The last one, though, is one to kind of trick you, where 0 goes to -4, 3 goes to 1, 4 goes to 5, 9 goes to 7, 3 goes to 1. You're supposed to look at this and say, wait a second, 3 is used twice. Isn't that bad? But notice that both of them go to 1. So even though we wrote it down twice, it's actually the same part, the same ordered pair. 3 goes to 1. X is 3, Y is 1. So this is okay. This is like saying John went to Stacy's house and John went to Stacy's house. You just said the same thing twice, but John is going to one house. John is not getting ripped in half and going to two different houses. And so this one might seem a little weird that 3 is listed twice, but because it goes to the same place, this is still a function. All right, now the vertical line test is a nice convenient way to check if something is a function when you see the thing graphically. So given the graph of a relation, you can test if it is a function by seeing if a vertical line passes through more than one point on the graph. So if the vertical line passes through more than one point on the graph, it is not a function. So the first one we see, this vertical line, let me use the highlighter here. This vertical line only touches the graph once, and no matter where I put a vertical line, it's never going to be touching the graph in more than one spot at a time. But notice in the second one, the vertical line drawn touches the graph at 2 points, right? Up here and down here. And so because it touches at 2 points, that is not a function. So now let's think about why using what we learned in the tables. If we were to label hypothetical coordinates for these 2 points, this top one might be 1, 2, where the x value is 1, the y value is 2, and the bottom one might be 1, -2. But notice this is two different y values, 2 and -2, because one's high up, one's down low, so different y values. But the x value is the same, 1 in both cases, because they're on the same vertical line, which means the x value wouldn't change. And so if we don't pass the vertical line test, so if this vertical line touches twice, that is equivalent to having one x value, in this case the number 1 is what I chose, go to two different y values. So you cannot have one x value go to two different y values. And again, the circle is also not a function because you can see the vertical line touches twice. And just to be clear, you only have to find one place where the vertical line touches twice in order to make it not a function. So on this middle graph, you might say, oh, if I put the line over here, it only touches once, but there only has to be one counterexample. Okay, so it doesn't have to fail the vertical line test everywhere. It just has to fail once and then automatically not a function. All right, so for number 4, it says state in words how to check if a graph represents a function. So really here, I just want you to write down the vertical line test again, what it does. So state in words how to check if a graph represents a function. What we are doing is checking, or I'll just write check here. So check if a vertical line touches the graph on 2 points. Okay, so check if a vertical line touches the graph on 2 points. Because if one vertical line touches at 2 points, that means you fail the vertical line test, just like the middle and right cases above. All right, now we're going to practice using this test real quick. So we're going to go real fast. If I draw a vertical line on the first graph, notice it's only going to touch the graph once, and so this is a function. The second graph, right down below, if I draw a vertical line, it's only going to touch once. No matter where I put the vertical line, it's still only going to touch once, so that one is a function. Okay, one way I like to do this, if you're in person doing this, use a pencil or a ruler, and essentially what you're going to do is the equivalent of what I'm going to do on my iPad, where you can take a vertical line, aka your pencil or ruler, and move it across the graph, and check if at any point along the graph it touches twice. So again, notice here, it never touches twice. So this once again is a function. Okay. The one in the top, we see a circle. It's going to touch that circle twice, so this is not a function. The straight horizontal line, no matter where I put a vertical line, it's only going to touch once, so that is a function. And the bottom right one, you might think at first, over here on the left, it only touches once. But if I move this vertical line side to side on the graph, notice in the middle here, it'll touch more than once. And again, you only need one place on the graph for it to touch twice for it to be not a function. So that one is not a function. All right, now we're going to find inputs and outputs. Okay, so functions can be presented in a variety of ways, and we need to know how to evaluate them given any of these presentations. So here we have several functions. We have g of x in the top. We have p of t in the middle in that table. We have h of x as an equation, and we have f of x is the graph. So what this problem is going to take us through is how to evaluate each of these functions. Okay, so we're just going to go one part at a time here. It says to find f of 2 for our first example. So f of 2, f is the name of the graph up here in the top right. Okay, so first things first, we got to make sure we use the correct function. So f is the graph. And on this graph, we want to evaluate the graph at 2. So what 2 represents here, 2 is the x value. So what I want to do is go to my graph and find out where this graph is when x equals 2. So what you can do is draw a vertical line at x equals 2 and see where this vertical line intersects the graph, which is going to be that big red dot I just drew. That big red dot is at x equals 2, y equals -1. Okay, the y value is -1 because you trace the dot over to the y-axis there. So f of 2 is the y value of that coordinate. So f of 2 is -1. So all you do to evaluate a graph is go to the x value that corresponds to the x value you're plugging in this case 2, and see where a vertical line at x equals 2 intersects the graph. Okay, for part B, it says determine x when f of x equals -3. This is the exact opposite, okay? We're trying to find x when f of x equals -3. So this -3 here is a y value on the graph. So what we want to do is go to that same graph, but do the opposite thing we did. Okay, so I'm going to delete my vertical line that was there. And what we want to do now is we want to draw y equals -3. So remember in previous lessons, we learned how to graph horizontal and vertical lines. This is one of the main reasons we needed to know how to do that, is you saw I drew a vertical line for x equals 2. Now I'm going to draw a horizontal line for y equals -3, because when you have y equals a number, that gives you a horizontal line. So again, this is y equals -3. The other line I had drawn earlier, if I label it, was x equals 2. All right, so now what we want to find out from this line y equals -3 is where it intersects the graph. So it's going to intersect at this point right here, which is the x value is -2 and the y value is -3 because that's what we set the line equal to. And notice I got that x value from tracing this green dot up to where it says -2 up there. Okay, and I'm going to add my other label to that other point. I deleted it earlier, but I want to keep it on there, 2, -1. Okay, so for part B here, it says determine x when f of x equals -3. We drew a horizontal line at y equals -3. We found where it intersects, and the x value of where it intersects is -2. So we can just go ahead and say that x is going to be equal to -2 when y is -3. All right, part C says g of 68. So the g function is the function in the top where we have a list of ordered pairs. G of 68 means that we are plugging in 68, so that 68 is the x value. So what I need to do is go to that list of ordered pairs and find the x value of 68, and that is the very last coordinate. Okay, if you look in here, 68 is the last x value we see. You might have thought it's this point over here, 58, 68, but that 68 is actually the y value, not the x value. So we want it where the x is 68, and the y value then is 24. So you can see from that ordered pair, the y value is 24. All right, for part D, we want to do h of -9. H is the equation 18x plus 26, so we actually already know how to do this one. To find h of -9, we substitute -9 in for x. So we're going to have 18 times -9 plus 26, where I'm just taking that equation of h of x and plugging in -9. When I simplify this is going to be kind of a big number, so let's pull out a calculator. 18 times, and then I'll put parentheses, -9, gives me -162. And if I add 26 to it, I'm at -136. Okay, so -136 is going to be our y value. And that's the one you guys are already familiar with, is just plugging in the x value to the equation. Okay, part E says P of 34. So that is referring to the table. Okay, the table is named P. And using the table is the same as what we did when we used G. We just have to find out where the x value, or in this case, the t value of 34 is, and then find the corresponding output value. So if I look at the table, the t value of 34 is that very first one. And if I look at the corresponding y value, it's the 93 that's right below the 34. So P of 34, where 34 is the t value that we're plugging in, this is equal to 93. And if you're confused on why it's t instead of x, we can use whatever letter we want for inputs and outputs. So generally speaking, we use x and y just because those are the two convenient letters. They're just nice, easy letters to write down. They look good on paper and all that. But really, you can name your inputs and outputs whatever you want. And in this case, we named the input t and the output p of t. But these are just names, okay? It's like every person has a name, right? So every function and every input can also have a name. And usually we use the letter t when we want the input to represent time. And we use the letter x for just general cases where x could kind of be anything. But usually we want to name the input based on what it actually represents. All right, and on that note, where the input could be anything, let's evaluate functions for all sorts of values. So we're not going to simplify any of these because a lot of them are going to be nonsense. Okay, but the idea here is to get you used to plugging in things that are not so simple. All right, so we just saw examples where we evaluated functions for specific numbers, but depending on the context, we may be able to evaluate functions for a lot of different things. So the idea of this topic is to get you comfortable plugging in things for x, even if it might seem wrong. We might always think of x when we say variable, but keep in mind that we can give the variable any name we want, and x is just the most common choice. So at number 7, it's not going to be too complicated. It says evaluate f of x equals 2x cubed plus 3x for x equals y. So instead of plugging in a number, okay, usually that y value right there would be a number like x equals 3, and we know how to plug in x equals 3. This time we're just going to plug in x equals y. So we are going to find f of y, where all we do is replace the x with the letter y instead. So I'm going to get 2y cubed plus 3y, and that's it. I don't have to do anything else, okay? All I did was replace each x with the letter y instead. All right, so now we're going to take that same function, f of x equals 2x cubed plus 3x, but now we're going to plug in x equals tree. Okay, so I literally drew a little tree here, and we're going to set x equal to that tree. Now, my doodle is not going to be quite as good as that doodle, but it's the same idea as what we just did for f of y. Okay, we're going to find f of tree. Okay, that's my tree. And so everywhere I see an x, I'm just going to put a tree instead. So it's going to be 2 times tree cubed plus 3 times tree. Where everywhere I saw an x, I just put a tree in its place. Now again, that might seem weird, but that's okay. It doesn't have to feel correct in order to be correct. And by that what I mean is, right now tree is meaningless. It's just a tree. But we might have somewhere else on our paper that tree is equal to, and then it might be a number, or it might be another function. And so that would allow us to then substitute in whatever tree is equal to for tree later on. So again, it seems weird, but let's make it even weirder. We're going to evaluate f of x equals 2x cubed plus 3x for x equals Samuel L. Jackson. Why not? Okay, so we're going to say that f of Samuel L. Jackson, should have chosen a shorter name, is equal to 2, and then I'm in parentheses, I'm going to write Samuel L. Jackson, and this is cubed, plus 3 times Samuel L. Jackson. Which again, might seem weird, and that's okay. I'm gonna move this down, by the way, that way it's all in one line. So let me put this over here instead, since it was a little long. So f of Samuel L. Jackson is equal to 2 Samuel L. Jackson cubed plus 3 Samuel L. Jackson. Samuel L. Jackson, I know is a person, but you gotta think about it's just a name for a variable. So we could define Samuel L. Jackson to be anything later on, and all this does is put a placeholder there where later on if I tell you Samuel L. Jackson is equal to 59, then we just replace the name Samuel L. Jackson with the number 59. Okay, so X doesn't have to be the thing we plug in all the time. We can literally name variables anything. We just don't tend to make it complicated like this, like Samuel L. Jackson, because why make it harder than it needs to be? But I assure you, eventually, if you go deep enough in things, you'll have names of variables that are absurd because you want to give it a name that makes it easy to understand what it represents. So it could be anything. All right, and then the last one, this is going to help you when you get to calculus, or if you are doing difference quotients in college algebra later on. You often have to plug in something that looks like x plus h. So just pretend that where we wrote Samuel L. Jackson, we're going to write x plus h instead. So f of x plus h is equal to 2, and then just like I put Samuel L. Jackson in parentheses, I put x plus h in parentheses, cubed, plus 3 parentheses x plus h. Okay, that is essential that you can do that. And the only thing we did was replace the letter x with the expression x plus h. Okay, so very simple, you're just plugging it in. But believe me, that is a very complicated thing for students down the line, because then in college algebra, what we would do is actually distribute. We would do this cube on the x plus h, and that's where everyone loses their minds. But if you can get through step 1 right there, which is to write x plus h in parentheses and put it where the x used to be, then you're in good shape. All right, we got one more title slide question, and then we're done with this thing. So back here at the top, says the number of tacos consumed at a restaurant with a number of customers P is given by the function T equals f of P. Last week, the restaurant workers saw 6,000 tacos get consumed by 2,000 customers. Express this information using the function f. So all we're going to do is replace T with the number of tacos and replace P with the number of customers. Because we're told in the first line that tacos is big T and customers is little p. So all I have to do is take the equation, T equals f of P, and replace the T and the P with what I know they're equal to. So the T is 6,000, and then I'll leave the equals f and the parentheses alone. The P was 2,000, so we have 6,000 equals f of 2,000. Meaning 6,000 tacos were consumed by 2,000 customers. So now we're going to turn that around. In the next line, we have explain the meaning of f of 2 equals 6. F of 2 is supposed to look like f of p, meaning the 2 is the letter p. And we always set f of p equal to t, meaning the 6 is the t. So p represents customers. So 2 customers. 8, and then the 6 represents tacos, so 6 tacos. Okay, so f of 2 equals 6, 2 customers, 8, 6 tacos, and you guys now have the introduction to relations and functions, lesson 12. Great job today, team, and I'll see you next time.